Another common problem in which we'll apply Newton's second law is something called an Atwoods machine. In an Atwoods machine, we'll have at least two objects connected by a string, and there's typically a pulley in our system, and the pulley serves to just change the direction of the string without changing the tension. In this problem that we'll look at in this video, we have two objects with masses of 3 and 5 kilograms, and they're connected by a string that passes over a frictionless pulley. The fact that the pulley is frictionless is really not too meaningful right now to you. It will mean a bit more as we study rotational motion. For our purposes right now, the importance is that the pulley does nothing other than change the direction of the string. That means the tension in the string is the same everywhere throughout that string. That's one of the things we're actually going to be looking for here, the tension in the string. In this example, we have two objects that are moving. My 3 kilogram block and my 5 kilogram block are both going to move. And if you think about this situation in the real world, the 5 kilogram block is going to go downward, whereas the 3 kilogram block is going to go upward. And so we're going to use that knowledge, the fact that these two things are connected, which means that they'll have the same magnitude of acceleration to help us find this problem. We always start off by drawing free body diagrams. In this case, we have two objects that are moving, and so we're actually going to draw two free body diagrams, one for each object. For the 3 kilogram object, we know that that one's going to move upward. More specifically, it's going to accelerate upward. And so I have a gravitational force acting downward on the Earth. And we know we have tension acting upward. And tension is going to be greater than the gravitational force. So now the block is accelerating upward. For the 5 kilogram block, we know that that one is accelerating downward. That tells me that the force of gravity on that 5 kilogram block is going to be greater than the force. Now, it's also important to note that these two forces of tension are going to be the exact same because it's the same string. And so they should appear as the same length in our free body diagram. Now, since I have two diagrams, I can write two net force equations. For the 3 kilogram block, the net force is the tension plus gravitational force, and I'm just going to put 3 here to remember the best for the 3 kilogram block. And that's equal to the mass of the 3 kilogram block times the acceleration of the 3 kilogram block. I can write the exact same equation for my 5 kilogram block, and the only thing that changes is that instead of the 3 kilogram block, it's now the 5 kilogram block. And so I'll put 5 subscripts on my quantities that have subscripts. Now, here's a couple of important things to note. First of all, as I've already mentioned, those two tension forces are equal to each other. And since those two tension forces are equal to each other, I did not put subscripts on either of these two t's. Also, these two objects are going to accelerate at the same rate. However, one is accelerating upward and one is accelerating downward. In other words, the acceleration of the 5 kilogram block is equal to the negative acceleration of the 3 kilogram block. I'm going to use that in my equation here. And so I'm going to rewrite the second equation to say that tension plus the gravitational force on the 5 kilogram block is equal to the mass of that 5 kilogram block times the negative acceleration of the 3 kilogram block. The reason I did that is so that I'd end up with two equations with the same two unknowns. Both of these equations contain tension as one of the forces, that is one of our unknowns, and both of these contain acceleration in them as being the other unknown. We can solve for those gravitational forces relatively simply using the equation gravitational force is equal to gravitational acceleration times mass, and we know the masses of our two objects. So we can set up a system of equations to be able to solve for these two unknown quantities. Specifically, I'm going to go ahead and solve for acceleration first. And I'm going to solve for acceleration by subtracting the two equations from each other. Now, this is just one skill, one algebra skill that you can do to eliminate one of your unknown variables. And it is not the only way to do so. So if there's another algebraic way that you prefer over subtraction of equations, that's totally fine. This is just one possibility. When I subtract equations, I always kind of subtract vertically here. So I have tension minus tension, which means the tension goes away. I have the gravitational force on the 3 kilogram mass minus the gravitational force on the 5 kilogram mass. And that's equal to the 3 kilogram mass times the acceleration minus a negative 5 kilogram mass times the acceleration. Since I have minus and negative, I end up adding those two together. And now, once I solve for these two gravitational forces, I only have one unknown quantity. I can solve for this acceleration, and then I can plug that acceleration back in for the tensions. My suggestion to you now is to pause this video, try to do this math on your own, and then once you unpause it, I'll provide the answers to you just so you can check your work. So you should have found the acceleration to be 2.45 meters per second squared. That's its magnitude. And of course, if we're talking about the acceleration of the 3 kilogram block, we would say that the direction is upward. And if we're talking about the acceleration of the 5 kilogram block, we'd say the direction is downward. You should have also calculated tension. And tension you should have found to be 36.75 newtons. In this case, once again, that's our magnitude. If we're talking about in either case, however, the tension is pointed upward. And so we could add that direction in kind of overall, since it's upward on both of our blocks. So any problem that we have two objects connected by a string and there's a pulley involved, we can apply this same process where we draw a free body diagram for each mass. We know that the tension is the same in the whole cord, and we know that our objects will accelerate at the same rate, even if those accelerations are in different directions.